Welcome to ECE 320, Electronics 1, lecture number 18, Semiconductor Relays, or SCRs. Now, an SCR is also known as a thyristor. A thyristor is a PN device, which can be thought of as a PNP transistor along with an NPN transistor. What that does is that produces a diode you can turn on and off. For example, if we go anode to cathode, there's no current flow, because through here there's a reverse bias diode somewhere. Now, if I were to apply a little bit of current at the gate, what happens is that applies current for that PN junction. This transistor turns on. That allows current flow, collector to emitter, through this diode, and I suddenly have current flow. As I have current flow through the base of the PNP, that allows current flow emitter to collector, which then turns on the NPN, which turns on the PNP, which turns on the NPN. Once I apply a little bit of current to the gate, the thyristor turns on and stays on. As soon as I ground the gate, turn off the current flow through this transistor, that blocks the current from the base, which blocks the PNP, which blocks the NPN. Once I turn it off, it stays off. Once I turn it on, it stays on. And there's a good example of that on YouTube. This is a semiconductor relay. And you've got the gate, and then the cathode and anode. Notice initially there's no current flow. What he's doing is he's touching his finger to plus 5 volts and the gate. That allows a little bit of current flow that turns on the thyristor. Once it turns on, it stays on. He then touches ground. Ground turns off the NPN, which turns off the PNP. That's the idea of a thyristor. It's a diode I can turn on. Let's show you that again. It's a diode I can turn on, apply a little bit of current to the gate. Your fingers are about 10 kilo ohms. So when you tie the gate to the voltage, it turns on. Apply 10 kilo ohms to ground, that turns off the gate. So again, it's a diode I turn on, turn off, turn on, turn off. And I can control how it turns on and off. That's why the symbol for a thyristor is a diode with a gate. If I apply current to the gate, that turns on the diode, otherwise it turns off. There's a reverse bias diode and no current flows at all. Let's see. And that we kind of talked about. So what I can do with that is I can vary the voltage of an AC to DC converter. For example, this is an AC to DC converter that we looked at before. I've got my 4 diodes, D1, D4. They turn on when the input is positive. D2 and D3 turn on when it's negative. The net result is at Vn, I've got a full wave rectified sine wave. And the average is 0.6366 times the peak voltage. This 5th diode doesn't really do anything right now, but it will in just a sec. If I make the top ones thyristors, and the bottom ones just leave as diodes, make the top one thyristors, or SCRs, what happens is this diode stays off until I apply a small current to the gate. Then it turns on. Likewise for D2. So what happens is if the microprocessor is watching the input and doesn't apply voltage until 90 degrees, diode 1 stays off until here I turn on. Then it runs. As soon as the voltage goes or current goes to 0, the diode turns off. Once it turns off, it stays off. Now nothing happens until I turn on diode 2. And then when it goes to 0, it turns off. Nothing happens until I turn on diode 1. So by changing the firing angle from 0 degrees to 180 degrees, I can change what percentage of the sine wave gets through. What diode 5 does is this is actually a min circuit. It's going to be the minimum of Vn minus Vn and 0, or max circuit. So when diode 1 and diode 2 are turned off, the max is going to be 0. Diode 5 turns on. The average voltage then depends upon the firing angle, going from 0 degrees to 180 degrees. The voltage average, if you integrate, works out to be the peak plus 0.7 over pi times 1 plus cosine theta minus 0.7. Easier to see on a graph. Essentially, as the firing angle goes between 0 and 180 degrees, The voltage that I see at the output, the DC voltage goes from about 12 volts down to 0 volts. So by changing the firing angle, I can change the DC voltage. What that does for you is a couple things. I can change the power going to a heater. I can change the speed of a DC motor. AC motors won't have any effect. AC motors based upon frequency, and the frequency doesn't change. The DC voltage, however, does change. That'll drive a DC motor. So there's actually some ads on TV for this heater that's better because it's analog. And all they did is they just added an SCR, or pulse width modulation, something like that to let you vary the voltage. Not a terribly expensive circuit, but with advertising, you can use it as a sales gimmick. In terms of resolution, it doesn't seem like you can do a lot between 0 and 180 degrees. If my input is 60 Hertz, like usually it is if you go off the power grid in the United States, half a cycle is 8 milliseconds. If you're using a cheap microprocessor like a PIC microcontroller we use in embedded systems, that runs at 10 megahertz, or 1 clock is 100 nanoseconds. 8.3 milliseconds corresponds to 83,000 clocks. So with the processor, I can change the firing angle to a resolution of 1 part in 83,000. I can very accurately control the firing angle. I can very accurately control the DC voltage. So SCRs are actually very useful in controlling voltage. And it doesn't just work at 20 volts, it'll work at 120 volts AC as well. So let's do a design example. Suppose I want to take a 20 volt AC, basically a power transformer, or a wall transformer. In class and lab, keep away from 120 volts AC. That's got a kick to it and can, give you a good solid shock. The wall transformers are quite a bit safer to use, so if you want to build a circuit like this in lab, use a wall transformer. Suppose I want the output to be 10 volts DC, and I want to drive a 100 ohm resistor with half a volt ripple. The design procedure is to first set the firing angle. The firing angle sets the DC voltage. I can then use L and C. These are filters. They reduce the ripple at V2. The first part is to set the firing angle. I want the average voltage to be 10 volts. The peak is 19.3. That's the 20 volt peak minus 0.7 volts through a diode. Shifted by another 0.7. Basically, the voltage goes down to minus 0.7. If I shift everything up by 0.7, then the peak is 19.3. Then shift it down by 0.7 to take care of that offset. That's the equation for the voltage. The average voltage should be 10. Solve for the firing angle, and I get 42.12 degrees. To set the ripple, I've actually got 2 degrees of freedom. I can set the inductance and capacitance to set the ripple. Currently the ripple is 19.3 volts peak to peak. The peak is 18.6 right here. The minimum is minus 0.7, gives you 19.3 volts peak to peak at 120 hertz. I want to reduce it down to 0.5, so let's just use L to reduce the ripple by 10 times arbitrarily. Yeah, 10's a nice number. What that means is in the voltage divider, pick the inductor to be 10 times R. What that does is when you get to voltage division, I've got your R1 over R1 plus R2. If the inductor is 10 times R, the ripple would be reduced by about 10 times. That'll reduce, or that means, so pick L to be 1.32 henries. And the ripple is now 10 times smaller, 1.93 volts. Now to find C, I want to reduce the ripple by a factor 3.86. Go from 1.9 volts down to 0.5. So that means I want the capacitor to be 3.86 times smaller than the resistor. The resistor is 100 ohms. I want the capacitor to be 25 ohms, meaning C is 102 microfarads. So this is your final design. C is 102 microfarads. L was, I forget, 1.32 henries. Firing angle is 31 degrees. To simulate this, Circuit Lab doesn't do SCRs, but I can simulate in MATLAB. To simulate, I want to write the differential equations that describe the circuit. For the voltage, where my state variables are the current through the inductor, that sets the energy here. The voltage on the capacitor, that sets this energy. So my state variables would be I3 and I2, or B2. The change in variables, B equals L di dt, L I3 dot is this voltage. That voltage is V1 minus V2. The current I2 is C dB dt. I2 is I3 minus V2 over R. That gives you two coupled differential equations. To solve, what I do is, given the initial conditions, find the derivative of I3, find the derivative of V2, then integrate. This is Euler integration, not the best form, but it works fairly well. Keep the sampling size small. If I do that for a couple cycles, this is what you get. Here's the input V1. That's my half-rectified sine wave firing at 31 degrees. Here's the output. If I zoom in on the output, that's what it looks like. And that's just what I wanted. The average is 10 volts. And the ripple is a little bit less than 500 millivolts. That's because we're using slightly conservative designs. If I want to get more accurate, throw it in Circuit Lab. Or, given this, if I want to adjust the ripple, just scale capacitors. There are other variations on the circuit. If I want to save some money, I can get rid of that fifth diode. That fifth diode I kind of like, because what that does is it makes the voltage here the maximum of Vn minus Vn and 0. So this voltage can never go below 0. Take out that diode, V1 can actually go negative. What's happening is the inductor keeps the current flowing. If diode 1 hasn't been turned on yet, then diode 2 has to stay on. Even if the input voltage goes negative, diode 2's got to stay on. So I can't get negative voltage for V1. And now what happens is the firing angle goes between 0 and 180 degrees. Well, if I have, say, a 30-degree firing angle, the diode 1 turns on right here. It has to stay on until diode 2 turns on. Then diode 2 has to stay on until diode 1 turns on. So I get this negative voltage. Taking out that diode saves a little bit of money, but I get a bigger ripple. The peak-to-peak ripple goes from here all the way down here negative. And at 90 degrees phase shift, I'm down to 0 volts on average, because I'll fire at 90, won't turn off until I get over here. So my resolution drops. I can no longer make sense to make the firing angle go between 0 and 180 degrees. Now it goes between 0 and 90. Just a different way of doing it. Some circuits use the 4-diode model. Some use 5. If you use the 4-diode model, then the average voltage will be the peak, or the 1 over pi times the peak, times 2 over pi, times cosine theta. And the peak-to-peak voltage will be the peak right here, plus that distance. A design example. Let's repeat the previous design. Suppose we want to output 10 volts DC at 500 millivolt peak-to-peak ripple, driving 100 milliamps. In this case, I'm going to calculate the firing angle when I don't have diode 5. So I want the average to be 10 volts, so the firing angle is now 32 degrees. And this is what the voltage is going to look like. It's going to go from 10 volts up to 20, down to minus 10. Then the second diode turns on, jumps up to plus 10, bias goes to minus 10. The ripple at V1 is now 28 volts peak to peak. If again I make the inductor, choose the inductor to make the ripple 10 times smaller, it's the same as we had before, 1.32 henries. Now the capacitor has to be 5.7 times smaller than R. So instead of 100 ohms, it's now 17 ohms. So we need a bigger capacitor. And if I do that, again I get a very similar design. The voltage should be 10 volts on average. And the ripple should be about 500 millivolts. Again, our design's a little bit conservative. So I'm actually only getting about 0.2 volt ripple. But it's similar to what we wanted. And the corresponding MATLAB code, that's in the lecture notes if you want to see it. So that's lecture number 18 for ECE 320. Semiconductor relays, a way to have an AC to DC converter where it can vary the voltage at the output.